Okay, I would like to talk about the homework. So solution for the last homework. So basically, the first problem, I asked you to extrapolate a signal that have a 50 samples. Say it's basically a sinusoidal signal, and extrapolate to have 20 more samples. So a total of 70 samples. And we assume that it's a Gaussian process model, and the rule there is 0.5. The rule is basically the correlation coefficient between adjacent samples, and here we also assume the variance is 1. Basically, is the as you can see, the variance of the signal itself. And so in other words, like basically we'll have a let's see. So we have a signal is like this one, right? So we have basically the coherence matrix will be a size of like 17 by 70, and the diagonal will be all 1. That basically it's just the variance of the signals. And then the off diagonal, the first off diagonal will be just rho, is the correlation coefficient between the two adjacent samples. And because we have a Gaussian process model, we have a Markov property that like given, for example, like the correlation coefficient between like these two guys will be equal to the correlation coefficient between these two guys multiplied by these two guys. So that should be rho square. So therefore, like the legs off diagonal will be rho square, and also the other side will be rho square as well. And if we can, by the same manner, for this one and this one, the correlation coefficient will be rho square multiplied by rho will be rho cubed there. So therefore, the coherence matrix will be a diagonal with all ones, and the first off diagonal will be rho. Of the upper and lower are both rho, and then the second off diagonals will be rho square, and the legs off diagonals rho cube, and so on. Now we assume this is the coherence of all the signals, like 70 samples there, and we are given the first 50 samples, so we will say the first 50 samples is x, and next 20 samples as y. So then we'll partition the coherence matrix as like this sigma xx, sigma xy, and sigma yx, and sigma yy. So the sigma xx will be 50 by 50, sigma xy will be 50 by 20, and sigma yx will be 20 by 50, and so on. So then by what we kind of discussed in class, once we have something observed, basically x is observed, the remaining y, we'll have a distribution is also Gaussian. So y given x is Gaussian, and also we know the mean is basically, already write it down here, is equal to mu y plus sigma yx, sigma xx inverse x minus mu x. So mu x and mu y here is the original mean of these signals. We'll assume that mu x and mu y is just zero means here, so that mu x and mu y is not here. So x here is basically sinusoidal. There we assume it's a sinusoidal. It's like this one here, the sinusoidal, I guess. And then sigma xx is basically this part of the coherence matrix, and sigma yx is this guy here. And then that is a Gaussian with mean is like this, and the updated covariance will be sigma yy, this guy, minus sigma yx, this one multiplied by sigma xx inverse sigma xy. And so then we have both the mean and the covariance of the new the conditional y given x there. Then the variances of these samples will be just the diagonal. Then we can take the diagonal and take the square root of that, we get the standard deviation. So then we can plot basically the estimated mean here will be the signal, the interpolation. Basically we have something like this, the signal here, and then wait a sec, I think it's a 50 sample, the it's 20, so I guess it's more or less like this. Then we continue to interpolate here, interpolate here. So here we get the mean is basically something we got a mean there, and then we can compute the variance of standard deviation. We can add and subtract the standard deviation from the mean to get an upper and lower bound. So it will be something like this. So let's look into the code that we have here. See. Yeah, that's a simple MATLAB code. This is the original sample. Here is a x, original signal, and then the first we set the n, the total samples is 70, and then let's see, and then we fill in the covariance matrix. Covariance matrix is like this way. The diagonal here I fill in the off diagonal for each of the off diagonal. You see the diagonal like this is up. Basically, I think it's the upper I off diagonal, and this is lower I off diagonal, and we'll fill that in rows I over to the power I, right? And then for the diagonal is just 1. So then if you look at C, therefore C is just like something like that, where the diagonal is all 1, and the next is row square, and so on and so forth. And then M1 is the length of X. It's like the first 50 samples, so M1 is like just 50 here. And then N2 is the remaining samples, so that first 20. So we got CX, XY, and CYY from this entire 70 by 70 covariance matrix. Then the mean, as I said, like from Y be like just inverse like CX6 multiplied by X, then multiplied by CYX, and then CYY will be given like this again. Then we take the diagonal is the variances, and we take the square root, and then we can plot the result. Y is the mean, right? So we plot from 1 to n, we plot like X and Y. Let's see. Let me see. Oh yeah, yes, right. 1 to n, like X is like the first 50 samples, the original, the input 50 samples there, and then we extend that with Y, right? That's the estimated one, and then we plot it blue, and then we plot another one is X and Y also, but we give a upper bound there for the first 50 samples. We add 0 to that. For the next 20 sample, we add the standard deviation as. So similarly, we do the same thing, but subtract like as instead. So then if you look at this here, okay, so basically here. So this is like the sample here. If you go down, you see it kind of try to extrapolate that, but because we assume the signal is still mean, right? So and also because it's Markov in the sense like given like the sample here, for example, if I try to predict what's the sample next here, given sample here, it doesn't care about what we have like earlier on. So therefore, it's quite reasonable that you just have eventually you will get to zero means as you continue to extrapolate, because the pi is basically zero, so you don't have any information which just decay to zero. But for the early one, we're trying to like kind of like smoothen that from like somewhere and get to zero whatever. And we can try different what was the effect if we change the wall there. For example, we have a larger wall, then it will be more sticky, I believe. So you get let's see, sticky in the sense that it is more effect for the for this sample here. So it decays slower. Maybe I can just even get smaller wall here. Let's see it. Yeah, so this decay even slower. So in a sense, like it does not do extrapolation as good as I expected, I hope for, but if you think about that, it's quite reasonable as well, because you're assuming a Markov again, they are assuming a Markov property is satisfied. So if I try to extrapolate this, like given these samples here, the early samples is actually doesn't give you extra information for this extrapolation. So predicting this guy, actually only the last samples give me useful information. But anyway, this is what we have. I guess I do have more questions here. Like we observe changing wall, we have something like this. And we also ask to try to verify that, or try to see for after the extrapolation. So look at the 51 and 52 and 53 samples. We want to see if that these three samples are still kind of satisfy the Markov property. Basically, the 51st and the 51st sample is conditionally independent given the 52nd sample. And we can verify that knowing that we have this result in class. Again, we also mentioned this earlier, that if you have conditional independence of x and z given y, then let's see what is for xy given c, let's say y given c, then in this case c is in the middle, then the correlation coefficient between x and y for xy will be equal to the product of xt multiplied by yc. So let's look at the covariance matrix. The conditional covariance matrix, that basically is CYY there. CYY. So if you look at the variance there, okay, maybe I change back to 0.5 and run this again. Of course, it doesn't matter, honestly. I assume that changing this won't affect this property of whether the extrapolated samples will be satisfies the Markov property or not. So, but anyway, I use the original wall there, wall equal to 0.5, and try to compute the correlation coefficient. So, but first of all, I have this matrix should be 20 by 20, right? And also, let me just show it once more. And you see the diagonal here is not 1. So basically, it's after the extrapolation, the original samples, well, we assume the variance is equal to 1, but as we have more information from the observed samples, so the variance should decrease, right? So this is another interesting observation you can make. If it's easier to just look at the diagonal. The diagonal have variances like that. So you see, like, the diagonal eventually have a variance close to 1. So that's the variance without any observations. And of course, for those that are far away from the observations, it will be like almost very close to 1. That's what we kind of anticipate. But for the one close to the observation, the variance will kind of decrease. So because we have observed something on one side, so the variance got decreased a little bit. So here, yes. Again, we want to check the correlation coefficient. And remember what's the correlation coefficient. So for example, we have a time course matrix, like, let's say sigma have a form like sigma xx, sigma xy, sorry, sigma yy, so what I'm doing, sigma yy, sigma zz, right? And this is like sigma xy, sigma xz, sigma yx, sigma yz, sigma cx, sigma cy, right? And so then I can write this thing. Basically the correlation coefficient is defined as like let's say rho xy is equal to sigma xy over sigma xx sigma yy. So therefore, in other words, I can rewrite this as a sigma xy is equal to sigma xx sigma yy times rho xy, right? So I have this is sigma xx square root sigma xx sigma yy times rho xy, right? And this one is sigma xx sigma zz rho xz. Yes. So in other words, the whole matrix will become if I in terms of like sigma x against sigma y, I'm in terms of rho xy and so on, then I will have something like this: sigma xx square root sigma xx sigma yy rho xy. I need more space, and this is a sigma xx sigma zz rho xz. This is a sigma xx sigma y rho xy. Actually, this is the same thing. This is a sigma y here. This is a sigma y sigma cz rho yz, and then sigma xx sigma cz rho xz square root sigma xc, sigma yy sigma cc rho yz. This is same thing here, and sigma cc. Okay. So it looks a little bit ugly, but knows that if I divide each row by sigma xx, so if I pull out sigma xx from each row, from this row, and sigma yy from this row, and sigma cz from this row, square root of that, I'm also, this column, if I pull out sigma x square of sigma x square sigma y and sigma z from these rules. I'm also pull out sigma x square root and sigma y and square root sigma z from these columns. Basically, I will just have 1 rho xy, rho xz, rho xy, 1 rho yz, rho xz, rho yz, and 1. Or I can, what is this? I mean extract or like pull a factor of like sigma square sigma x square x y and square sigma z here is basically the same as saying multiply this guy by, let's see, multiply this guy by square root sigma x, sigma y, and sigma z, right? So if this one multiply by this, I'm basically, in this case, each row, I'm basically multiply sigma x square, sigma x on this row, sigma y on this row, and sigma z on this row. And also if I multiply on the left hand side, would be like multiply this column by square root sigma x here, sigma y here, and sigma z here. Yeah, okay. So, in other words, if I do a reverse of this operation, so if I multiply this by square sigma x, square sigma y, and square sigma z, I should kind of like make the diagonal into 1, so I can multiply this one over 1 for sigma x, sigma y, 1 over sigma z. I'll get from this form, I'll kind of normalize the diagonal into 1 and the off diagonal to be all row. So let's try to do that. So what I mean is I get the diagonal is those sigma x, sigma y, and so on. So that's why it's let's call it diagonal just D here. Diagonal CYY. And I want to take a square root of that. And also make it a diagonal matrix. Oh, wait a sec. I want to make it 1 over that first. And take it as a diagonal matrix. Then I get a matrix here. Let me just give a name for that. Let's call it U, whatever. And then if I have like U times CYY times U, it should give me the diagonal equal to 1. Yes, looks like it's okay, right? Diagonal is 1. That's good. So, that means that like the off diagonals will be the correlation coefficient. So, for example, like if I look at the 51st and no, this is already like the condition. This for example is actually the 51st, right? 52nd and so on. So therefore, like this one is actually the correlation coefficient between the 51st and 52nd samples, and this one is the correlation coefficient between the 52nd and 51st samples. And this will be the correlation coefficient between the 51st and the 53rd sample. And so what we expect is that we should have therefore like let me give a name of this matrix again. Maybe just a big row here is this guy, row 1, 2. These are the the correlation coefficient between the 51st and 52nd. Row 2, 3 will be correlation coefficient, this guy here, between the 52nd and 53rd. So if the conditional independence is satisfied, we expect that this multiplied by this guy should be equal to this guy. So we just check that. 2 should be kind of equal to 1, 3, right? So it looks like it's pretty correct, right? It's like this should be just numerical error, 10 to minus 17. So numerically we can verify that like this conditional independence is satisfied still after the, I mean this is kind of reasonable. Like you have the Markov property at the beginning, even you have these observations from the you may break the Markov property if your observations. So basically you have like samples. Think of like you have samples like this, have the Markov property here, your observations here. The Markov property for these samples will be kind of violated after having this observation. But on the other hand, if like if you have Markov property for between these two guys here, if you make an observation here, I will guess that the Markov property between these two guys will be violated. I will leave this, like maybe just have you to verify that. So anyway, so let's look at the second problem here. So the second problem is that very simple one. We say like try to look into a Pyro. I just want you guys to try to play with the Pyro and basically get all the pull out the spreadsheet here. The Jupyter notebook here. This just an introduction of Pyro for use for inference, and this notebook actually we also discuss in class. It's a very simple like inference problem that we have a kind of like a Pyro. Okay, basically it say that okay, we're trying to take some measurement. We have some actual weight. It's like Gaussian distributed with a prior. They call it the prior is called as a guess with a standard deviation of line. So this notation is a little bit different. They from the what is in class like Gaussian guess like 1. If I believe that this is actually is understood as like the standard deviation rather than the variance. So this has to be careful. Usually, like when you have Gaussian something like a number here, it has to be because I don't think the convention is kind of standardized. Like some people will consider this as a variance, consider this as a standard deviation. I believe like here they assume this is the standard deviation with standard deviation 1. And this is the ground truth there, the true weight there. But then we make a measurement, and that measurement it's kind of like we have a Markov property here. Given the actual weight here, we don't care about the prior guess there. So it's a Gaussian again, like with the mean is equal to weight, and then like the standard deviation is 0.75. Now we want to do for this very simple like kind of inference problem. We have the gas here and we have the measurement here. We want to find the weights there, and it's very simple actually. We know that we basically have a cosine solution in this case. So basically we have the gas here. Let's see. Let me just write down. So we have the weight is a gas. The standard deviation, let's say a similar weight, maybe just call it similar weight square. This is the prior. This is a pi variable, I can say, and W is the true weights there, and then like I have the weights is have a distribution like this, right? Or maybe the more common notation will be like this. It's a Gaussian distribution with that. Then I have the measurement. It could be just depend on the weight, right? And the variance is like, let's say I call it sigma m square. Now then we are given the prior here, G here, and given the measurement there, and we want to find the estimate for the W. And in that case, it's just you have P. This is basically say we have this is like the P, or like maybe I should write P. W given G is equal to NW G sigma W square, and then we have P M given W is equal to like W W W sigma M square, okay? Then if we have a map estimation, anyway, if we compute the posterior, it will be the product of that way, or the posterior PM given WG will be proportional to, or maybe I just write a constant multiplied by PW given G, PM given W, right? If I multiply, because if I multiply these two guys, it will be P. Or maybe like let me write the whole thing out. So this will be like P M W times how do I write it? Yeah, maybe I write like this over P W given G, right? So this is just space rule here, right? So we have P and W given G over PW given G here. So if we want to get the best estimate of wait, something doesn't look right here. Oh, of course, because I'm sorry, I'm not estimating M, I'm estimating W, right? Estimating W. So we have the measurement, we have the pi, we're trying to estimate the W. So this here above is correct, but I want to have P given G instead, right? Then this is equal to P M over W multiplied by P W given G. Right, it's just on here. Actually, you see this, or like if I want to write more clearly, this will always hold. This is just a kind of base rule again, right? But because of the Markov property, given W, like trying to estimate M, like we don't need to know G, so like this is gone. So I've got this, it's just this guy, it's just this guy is a Gaussian distribution, and this also is a Gaussian distribution. And so therefore, let's see if I can erase something. So therefore, and therefore if we try to estimate W, so let's say I have map estimate, I want to up max this guy, so PW given mg. Now then this does not depends on W, right? So the denominator I don't care about it. So and then what I need is just to care about the upper terms here, because only the upper terms depend on W, and I can write as some, or like if I don't have upmax here, I can write this guy is equal to some constants times P given diff W times P W given G. And for Gaussian, we know that like if we multiply these two guys here, so can like multiply these two guys. If you remember, like when we multiply this two Gaussian distribution, it will still be a Gaussian-like. Of course, in general, this doesn't need to be a distribution anymore. Maybe I should say it more clearly first. Like if I try to multiply, okay, for this guy PM given W is a Gaussian W sigma m square, right? This is a n W G sigma W square. So if you look at both this guy, like this one is a variable W with mean G and sigma W square as variance, and this one is a kind of distribution of M with mean W. But distribution of M with mean W is the same as, if you look at the PDF, like it's symmetric, right? This PDF function is something like exponential, like M minus W square. Okay, let's don't try to. Let's try to write better, like this, right? So with some constant here anyway. Whether you consider this as a PDF with variable M and mean W, or like a PDF of variable W and mean M is the same function, right? So therefore, like I can also write this as WM, right? Now, so then it's like product of two PDF for variables W, and the product of that PDF is two Gaussian PDF is still Gaussian-like, but of course, like in general, it doesn't need to be normalized. If you multiply these two together, actually what you get is you have some constant, some normalization factors coming up. If you remember, like that normalization factor turns out is equal to M G sigma M square plus sigma W square. So therefore, actually, this is the nice thing. Like if I compute this product, I immediately know that what is K is. K is actually equal to this 1 over. Let's see. K is actually equal to 1 over this guy, I believe. Because like this multiplied by this is equal to this guy here. Sorry. this multiplied by this is equal to this guy multiplied by something here, but that is the PDF for M, and should normalize to 1, and for this guy here, it should also everything on the left hand side here should normalize. If I normalize over W, it should normalize to 1. If and this multiplied by this guy, maybe let me just complete this, then it become more obvious. So this multiplied by this guy is I have, this is the normalization factor, but I should also have like a Gaussian line with mean is equal to a weighted sum of the weighted by the position. Position is just equal to 1 over the variance. So therefore it's a m over sigma m square plus g over sigma w square over 1 over sigma w square. Oops. 1 over sigma w m square plus 1 over sigma w square. Okay, I have no space again. Let's create some more space. And the variance will be equal to, or the position will be the sum of the position. So therefore the variance is equal to 1 over the sum of the position. So it's sigma m square plus 1 over sigma w square. Yeah, something like that. So what I'm saying that this multiplied by this guy is equal to this guy. But for this expression here on the left hand side, if you try to normalize over W, I mean integrate over W, it should normalize to 1. And for this guy on this side, if I so therefore like wait a sec. So therefore and for this part here, this does not depend on WA, but this part here, if I normalize over, this also normalized to 1, right, for W, because it's a PDF just on W. So therefore actually we see that this is actually equal to this guy, really. So that means that like K should be equal to 1 over this guy. So if K is equal to 1 over this thing here, so if K is equal to this guy, this multiple is this guy, right? These two multiple together equal to this guy, and multiplied by this guy, this got cancelled equal to this one also. So then like this also normalized to, so but okay, what I want, this is not something related to this problem in particular, but I just want to re-emphasize that it's often very convenient to ignore the normalization factor first and just move on and see like what's the PDF and what was the statistics of that PDF, what's the mean and variances, and the normalization factors can be figured out like later on. And in this case, of course, I actually don't need the normalization factor really. I don't need to know that because I just want to do an estimation for the mean and the variances, and that's basically these terms here. So therefore, like if I have the Pyro G and have the measurement M, actually I can have a best estimation, that's basically the mean of the PDF here, is just equal to this guy here. So I can write better, like, so my estimate, maybe I will write here, my estimate should have like m sigma w square plus g sigma m square over sigma w sigma m square, something like that. If I the variance is a sigma w square sigma m square sigma w square sub sigma m square, like this. And okay, what I asked you in my homework problem is I just try to go through the spreadsheet and try to the original spreadsheet here, assume the observation is the measurement is 9.5, right? Yeah, measurement is 9.5. Actually, you can see that measurement is 9.5. I want to ask you guys to change to 10 and see what happened, and then get the analytic estimate of the true weight. And these guys we can compare first, actually. Maybe I just compare it here, maybe. So we already had from here we know that like sigma, I can't forget, like the prior reference is 1, so sigma w sigma w is 1, so the sigma w is 1, sigma m is 0.75, this is 0.75, and the gas, let's see, what do we use for the gas? I think it's 8.5, right? You say like, the price is 8.5. You can see, like, let's see, as I said, yeah, they specify here in the code also. Gas is 8.5. So this is 8.5. And the measurement originally is 9.5, right? Originally 9.5, I want you guys to change to 10. So even without looking into the code here, we can get the analytical result. That is, maybe I put it here. Do I have a variable mg or something? I've got gas. I have a value gas here. Maybe I just use here in the bottom. I say m is equal to 10 and g is equal to what's it called, 8.5, and I say like sigma w is equal to 1, sw is equal to 1, and sigma m is equal to 0.5, right? 0.75 or like and then the mean, therefore the estimated mean for the weight will be g times sigma m square. Actually, I'm not certain that was the notation in Python. I can't forgot about that. Sigma m times sigma m, right? Or sigma w times sigma w. Wait. Yeah, g sigma m. It's okay. Sigma m times sigma m plus m times sw times sw and over SW times SW plus SM times SM. Okay, this is 9.46. So I should have the new estimated weight should be 9.46, and the estimated variance should be this one, right? Sigma W squared sigma M squared over sigma W sigma M squared. So we say SM times SM times SW times SW over SW times SW plus SM times so I say 0.36. So let's try to how to make the change. It says 46 is 0.36. Wait. Oh, I need to take a square root for that. So this is the you're trying to you want to so it says 0.6 basically. That's correct. Actually, I should the estimated standard deviation doesn't change, right? Because I didn't change the sigma S, sigma M, and sigma W, so it should be the same. It's still 0.6. So this one doesn't change, still 0.6. But this guy here, I changed to 0.46. Let's say, oh sorry, 9.46. 9.46. Okay. That's the analytical result. But let me change the measurement. Let me quickly change the measurement. The measurement is 9.5 to 10. Let's see where it's 9.5 here. So there's a 9.5 here. Is the conditional scale measurement 9.5. I'm not sure I use this here. There's some 9.5 here, 9.5 here. So sorry, but this is common. It doesn't use it. Oscillation 9.5 scale observation. This is this guide. Actually, I don't think we need that. Like, this is a perfect guide. Like, this is something to do with the variational inference. That you need to have a guess PDF to start with, but this guess can be wrong. Actually, in this case, I just assume this can be wrong. So I just changed the other 9.5 here. I think it doesn't use here. Let me just make sure that I don't think it actually use this scale observation function here. Yeah, it doesn't use this one. I think it only use this one, the conditional scale here. Let's see. Conditioned scale. The default condition scale. Yeah, condition scale is used that here in the model. So basically, if I just changed here, I'm supposed to change the oscillation. Let me just change it to 10 here, and then let's run the entire thing. So we guess pretty reasonable, right? It's not perfect yet, but it's pretty close. So that's the our analytical result. This is using Pyro. Our guide here is not perfect, but I don't think it actually I forgot that. And this is the estimated standard deviation. It's reasonably close as well. So that's basically. Do I ask you guys to do something more? Yeah, it didn't ask you to do more. You try to change the oscillation in the Pyro, we did that, and get the analytical result, we did that as well. So that's basically it. So okay, I'll just stop here then.